Welcome everyone. We're so excited. Today we're going to be looking at instantaneous motion. So we're looking at instantaneous velocity and instantaneous speed. Sounds like a big word, but it's really not. Let's get going, shall we? So, there we go. We are needing to discuss the difference between the terms average and instantaneous. Average is okay. Average we've heard about. You hear that when you get marks back. Your average for the term, average number of marks, average this. Instantaneous is a different kind of word that we think of like instant coffee. Happens straight away. Okay, so instantaneous, something that's quick. So, we have been looking, we've done vectors and scalars, we've done frames of reference, we've done position and displacement, we're busy looking at speed and velocity, okay? So that's where we're at today. There we go. So what are our keywords? Well, instantaneous speed, instantaneous velocity, and there'll be two different things, average speed, and average velocity, and then uniform speed. Uniform is a word we use quite often in this section, so we've got to remember what uniform means. Uniform means all the same. So when we talk about uniform speed, we're talking about constant speed, okay? So, there we go. Let's look at speed and velocity in detail. So this is what we're looking at. We need to be able to define speed and velocity, okay? We are going to look at what uniform means. Then we're going to look at what non-uniform means, which is where we're going to find the instantaneous. And then we're going to talk about average speed and velocity. We have to separate speed and velocity because speed is a scalar, no direction. Velocity is a vector, so now it has direction. They are different. They can have the same value, but they don't always because of the direction. So, and then of course we've got our calculations. We can't forget those. We're doing physics. So, speed is the rate at which, okay, so there we go, rate means time at which an object covers a distance. So it's how fast or how slowly it covers a distance. Uniform speed means it covers equal distances in equal time intervals. So if it's got a uniform speed of 1 meter per second, it covers 1 meter every second, which is about as fast as I walk some days. Average means it's the rate at which the total distance is covered. So average means that I take the whole distance and divide by the whole time, okay? An average will be bigger than the smallest, but smaller than the biggest. It sits in the middle somewhere. All right, with average though, you can't do it like in maths where you take the first number and the second number and you add them together and divide by 2. Because speed we might have a slow speed for a very short period of time, but the high speed for a very big period of time. It all depends on how long those speeds are. Well, how long we keep those speeds up for. I think that made sense. So, instantaneous. It's the speed of an object at a specific instant in time. It's actually really difficult to measure it unless you've got really nice, accurate electronic measuring equipment, all right? So it's the time it takes for an object to move in a very, very, very tiny time interval. So like in 0.1 seconds, or even smaller than that, 1/100th of a second. It's a little difficult to measure, but we're going to work it out through another method, which is easier for us, okay? So, speed, when we calculate it, is distance divided by time. Average speed is total distance divided by total time. You need to be careful. There isn't a symbol for these. Okay, you need to use the words. Velocity, still rate of change. So we're still involved with time, but now it's position. So that means we've got to take direction into account. Okay, that's the important part there. Uniform means that we cover equal changes in position in equal time intervals. Uniform means that we can't change direction. If we change direction, velocity is changed. Average means total change in this is the biggest difference, position divided by total time. And instantaneous, again, is at a specific instant, small time period. So, velocity is change in displacement, change in position over change in time. We like this because we got symbols. Average, you have to have the line over it, otherwise it means instantaneous. Change in x over change in time, okay? So, lots of little bits and pieces that we've dealt with. The biggest thing to remember is that with velocity, it's change in position. With speed, it's change in distance. Speed's a scalar, velocity's a vector. We're going to take a short break, and then we're going to look at some things that will hopefully make this make sense for you. So I'll see you in a couple of minutes. Welcome back, everyone. Now, we've spoken a little bit about average velocity, average speed, instantaneous. Now, let's get into the nitty-gritty, into the specifics, so that we can fully understand what we're talking about, okay? So, what we're going to do is we're going to look at uniform speed and velocity. So, I've got a little animation for you. So, here we go. Now, what we're going to see is we have a person on Father Brown, on a bicycle, and we're going to start to move in. And what I need you to pay attention to is on the right-hand side of the screen over there, there's going to be a speedometer. It's simply something that allows us to see how fast he's going. Okay, so I'm going to let him start, and off he goes. And we're supposed to stop it when he goes past the umbrella. We're not going to. But as you can see, his speed is staying constant, and it's just over 3 meters per second. That didn't change. Now, that's a speed because I haven't put a direction in. We didn't say which way he was going. But if I go, well, he's going to the right, that means he had a constant velocity of just over 3 meters per second to the right. Does it matter how fast he's going? Well, let's see. Let's make him go a little bit faster. Okay, just because we can. So there we go. Ooh, much faster. And if you look there, he's going at 6. Still, constant motion. His velocity isn't changing. His speed isn't changing. Okay. That means it's constant. We can do one more. Let's try one more. Let's see. Oops, got to reset him. Let's see how. Okay, let's go to 10 just because we can. There we go. We're supposed to time how fast he's going, but we're not going to. I just want you to see. Oops, he's going at 1. That's not what I wanted. Went too far. There we go. Much faster. Much faster. But still going at a constant value. So he's still going, in this case, it's just over 8, it's probably 8.5. Constant speed, constant 8.5 meters per second, don't care about direction. Constant velocity, because we can, oh, and it finished. Constant velocity, because he was going to the right, okay? So he finished, he ran out of space, he was tired. Okay, so that's uniform. Let's talk about what happens when we have changing velocity and changing speed. So it's not the same the whole way through, and we want to be able to work out how we get the average and the instantaneous, okay? So I've got another animation to show you. So here we go. I've got a car, okay, over here. Now with this one, I can't change how fast it's going to go, but that doesn't matter. You're going to see the car going to the right, so we're going to take right as that direction, and it's going to speed up, so the car's accelerating. What I need you to take note of is what's happening on this graph, because that's the important part, okay? So let's see him go. There we go, he gets nice and fast. Off he goes. There we go. And done. Now, if we look at this graph, we can see as time goes along, he gets faster and faster and faster. So he covers bigger distances in the same time interval. So his velocity is constantly changing and his speed is constantly changing. If I wanted to get average, I would simply take distance divided by time. Okay, that would be the first thing I would do. I'd take the whole distance divided by the whole time. That gives me his average velocity. If I want to know how fast he was going at a specific point, we have to use what is known as the tangent. I need you to see what happens with this blue line. So if I go and I say, I want to know what the velocity is at that point, it's 6 seconds. This line has now drawn a tangent, this straight line. I use that straight line to find the gradient of the graph, of the straight line. That gradient gives me the velocity at 6 seconds, exactly at 6 seconds. So that's the instantaneous at 6 seconds. So if I could measure it, so like a speed camera, okay, which measures the exact velocity as you go past it, that's what that would do. If I go to 8 seconds, can you see the gradients changed? This has become more steep, which is what we expect because it's getting faster, okay? I get there, and it's even steeper. So as we go, this line, this straight line, gets steeper and steeper and steeper. To calculate average, what we could do is work out the gradient at every second, every point of this graph, calculate all those gradients, then add them all together and divide by however many we calculated. But let's be honest, that's a lot of work. It's just easier to take total distance divided by total time. You'll get exactly the same answer. Let's do some calculations on this though. So here we go. I took some screenshots of the motion. Okay, it looks a little different to what we just created. So this one goes a little higher, it doesn't matter. But at 5 seconds, I want to know what the velocity is. So at 5 seconds, here it is. I'm going to work out the gradient. When you work out the gradient of the graph, you can use any points on the graph as long as they physically sit on the line. When you have a choice, find ones that are easy to look at. So I'm going to use this point over there where my distance, so this would be my position 1, okay, my initial position is 0, because that's 0 over there. My time, so this is T1, is, so that's 2 seconds, is 2.5 seconds. Okay? Now we look at it, and if I look nicely, I can use any point. So I could use this point over here, but I look at the graph, and it's not quite on a line. So getting the distance is a little difficult, and we look all the way. In fact, this is why I chose this one, is this is nice dot on the line, where if I go backwards like this, and you use a ruler, that's where it sits. This is 50 because of the scale, so that's 60 meters, and my time is 5 seconds. We're finding a gradient, so we go gradient. In this case, please, and this is where it gets a little strange for us, because in maths, we would use y1 minus y2 over x1 minus x2. We can't use y's and x's in science because they have meaning, which is different to maths. When we look at the x-axis here, this is position. Sorry, this is the y-axis, not the x-axis. The symbol for position, we're using x, okay? So my gradient is the change in the x over my x-axis is now time, so it's changing time, okay? So we're going to go, we need to keep those two together and those two together. That means we're going to do 60 minus 0 over 5 minus 2.5. Please be careful here for me. I know, and you know, that 60 minus 0 is 60. But you've got to show me that you minus the 0, because the 0 is important. It has meaning for us, okay? We're going to need to use our calculators for this. So we get our calculator out, and we're going to go 60 minus 0 divided by 5 minus 2.5, and I get 24. So over here, 24 meters per second. At the moment, I have calculated an instantaneous speed. I want instantaneous velocity, so I need to add in direction. And if we think about our diagram, it was going to the right. Okay, so at this exact moment in time, it was going at 24 meters per second at 5 seconds, okay? Come here. Okay, it doesn't want to. Let's go there then. Let's see what happens when we get to 7 seconds, okay? So here's my 7-second one. 7 seconds, and the distance is over here. So if I look at that, that's 120. And we need to find another point that will work. And if I look at it, I'm still going to use that one. It makes sense to use the 0. And in fact, if you can use a 0 point, use a 0 point. Make your life easier. Don't try and complicate the calculations, because complicating them complicates them. Okay, complicating them makes them more difficult for you. Make it easy for you. That's what we want. So let's see what we've got. So my first position is 0, and my first time is 3. So that's 0 meters, that's 3 seconds. My second position is here, and we just saw that that's 120. And my, oh, no, that's not 3. If you look at that, that's wrong, actually. I'm hoping some of you noticed that's not 3. That's actually 3.5. So let's make sure we write it down right, otherwise we're going to get the wrong answer. Do you see that? It's 3.5. Be careful, okay? My second time we said was 7 seconds. Okay, well, we've got enough information. We're still going to find the gradient. Okay, which is my change in x over my change in time. So we're going to go 120 minus 0 over 7 minus 3.5. Now, I know that some of you probably don't need to show all the working on the calculator like I do. I just don't want any of you to get lost with where I get the answers from, okay? We don't judge how you do your calculator work as long as you get the answer, okay? And everyone does this differently, and I know I probably use the calculator slightly differently to the way you do, or your calculator has a slightly different setup. It doesn't matter. So I've got 120 minus 0 divided by 7 minus 3.5. Oh, and remember, we can't leave it as a fraction. So that gives me 34,29. Okay, 34,29 meters per second to the right. It's a steeper gradient. It's going faster. It's what I expected. Okay. We could do the next calculation. We're going to run out of time, so I'm not. But we could do exactly the same thing here. We have 9.5 seconds, and this would be 230 meters. And I probably wouldn't use this point because that time's a little difficult to see. I would use this point, 8 seconds, and 150. Maybe we can just do it. Doesn't want me to write it there. Stop it. There we go. Okay, now I can get it to write. So we would be going 230. So watch, it's going to write it. We'll do it quickly because it's important. Changing x over changing time. So it's 230 minus 150 over 9.5 seconds minus 8. Definitely need my calculator. Can't do this in my head. 230 minus 150 divided by 9.5 minus 8. And we get 53,33. Much faster. And that's what we expected, and it's a velocity, so it's going to the right. All the time it's going to the right, still positive gradient, okay? So, average speed would be my total displacement divided by my total time. So if we look at it, it's 240 divided by 10. Okay, so average speed, oh my word, I'm going to run out of time, is going to be 240 over 10, which is 224 meters per second. My average velocity is going to be 240 divided by 10, 240, that's 24. That's why you use a calculator. No, one. So that's 24 meters per second, right. Same value, one has direction, one doesn't. Welcome back, everyone. So we've done a little bit of investigation. We have seen from a graph, average and instantaneous. But of course, now we need to do calculations. Now we need to know how are we going to get asked this? How do we get examined this. So that's what we're going to look at now. All right, you ready? Good. So here we go. A car travels 100 meters east in 5 seconds. They want the car's average velocity, and then they want the car's average speed. So there's two things we need here. Let's start with the first one. The car travels 100 meters east. So my change in displacement is 100 meters. There's my direction. And my change in time is 5 seconds. Now, unlike when we do it with the graph and we have to have 2 points, that's already taken into account. Okay, so don't stress too much about the fact that you don't know the beginning and the end point. It's already done for you. So we want average velocity. We need to remember that average velocity has the little line on top of the V, which is delta x over delta t. So we're going to have 100 divided by 5. And I know some of you can do this in your head, and that's wonderful, but in exam times, in tests, sometimes we get a little nervous and we panic a little bit, so we're going to use our calculators, okay? That's why we have them. So, 100 divided by 5, and we get 20. But I asked for average velocity. Velocity is a vector. Vector means I need to have size and direction. Direction is the same as the displacement, so it was going east. I have to put east in at the end. Don't forget the direction. It's so easy because we get so used to doing stuff, but you've got to remember velocity is a vector. We have to put the direction in. Next question was, what was the car's average speed? We just worked out that the average velocity was 20. The nice thing here is that average speed and average velocity in this case is exactly the same. Why? Because the displacement and the distance they traveled was the same value. It's not a case of the car, it is a car, yes, the car traveled so many meters east and then went so many meters west and then so it changed direction and so the distance is different. The distance is the same. I don't need to calculate it again. So I can just say that my average speed is 20 meters per second. Remember, speed is a scalar, so direction mustn't be included. If you put a direction here, we'll mark it wrong because it's not showing that you understand that speed's a scalar. All right, next question. A car accelerates from 5 meters per second to 25 meters per second in 10 seconds. They want the car's acceleration, and we have looked at acceleration briefly in a previous lesson. So, this is my initial velocity. It's what it started as. The 25 is my final velocity. The time is 10 seconds. That's changing time. Now, it's been a while since we did this, so sometimes we've got to refresh our memories. Acceleration is the rate of change of velocity. So acceleration tells me how quickly or how slowly the velocity changes. That means acceleration is change in velocity over change in time. Whenever we do a change in, it's always final minus initial, okay? Please don't go, it's got to be big minus small. No. In science, change in means final minus initial, okay? So, my final velocity was 25. My initial was 5, and it took 10 seconds. Let's use our calculators. So we've got 25 minus 5 divided by 10, and we get 2. The units, meters per second squared. But acceleration is a vector, just like velocity. That means we need to give it a direction when we get to the end. We look at this and we go, but I wasn't given a direction. There's no left, right, up, down, east, west. We make an assumption. The car must have been going forward. And the acceleration is positive. The acceleration got bigger, so that means the acceleration must also be forward. That's what I'm going to use as my direction. That's fine. You could, if you wanted to be extra sure, go in the same direction as the car's motion. Watch. So I could have said in the same direction as the car's motion. It's the same thing. Okay? Good. Next one. Ooh, a plane accelerates down a runway. Okay, so it's accelerating down a runway, and after 29 seconds has a velocity of 260 kilometers per hour north. Yay, we've got a direction. Calculate the acceleration of the plane. All right, good question. We know time. We know final velocity, which is 260 kilometers per hour. What's the initial velocity? Well, it's accelerating down a runway. We can make an assumption that the initial velocity is 0. Okay? But that's meters per second. I'm hoping some of you are going, but there's a problem here, Tracy. I've got kilometers per hour, and we need meters per second. Well, we just need to convert it. So the way we convert it is we're going to take, so this is my conversion, 260 kilometers per hour. And we remember to get kilometers into meters, we times by 1,000. And 260 kilometers per hour means it's 260 kilometers divided by 1 hour. We then need to times by 60 to get it into minutes, and times by 60 again to get it into seconds. Okay? So I'm going 260 times by 1,000 divided by 1 times 60 times 60, whoopsie, not 600, that would be terrible, and we get 72,22. Okay, now I want to show you a trick. That is the same as taking this value and dividing by 3.6. Let's prove it, okay? So I'm going to take my 260, divide by 3.6. Oh, look at that. Same answer. So you can simply remember that you've got to divide by 3.6. Okay? All right, so acceleration is change in velocity over change in time. 72,22 minus 0 divided by, it's a very funny time, but that's okay, we'll take it. All right, so we've got 72.22, minus 0 is 0, so 29 is 72, not 0. Oh, look at that. So now we get 2,49 meters per second squared, but acceleration is a vector. Vector means that I need direction, and they were very nice because we know that it's going north. Okay, so we know it's going north. The big thing with this question, out of all the ones we've done so far, is this. We cannot work in kilometers per hour. We must work in meters per second. So either you can work it out the long way, or you simply divide by 3.6. Makes it nice and easy for us. We've done a lot so far, so we're going to take a short break, and then we'll carry on with some more questions in a couple of minutes. Welcome back. I hope we've rested. We've got our calculators and our pens and our pencils and our paper, and we're ready to do a couple more questions. We are? Good. Let's get going. So, question. A sloth. A sloth is it's an animal from Australia, and it moves very slowly. They have very long arms, and their babies are just too cute for words, but they move very slowly. They slow, okay? So it can get to a maximum velocity of 0,037 meters. A giant tortoise, now giant tortoises are those big tortoises, and they can live hundreds of years, okay? They live for a very long time. Can move at 0,076, so it's actually faster than a sloth, okay? So that's the information we're given. The first thing they say, if it takes the sloth 10 seconds to reach 0,037 meters per second, calculate the sloth's acceleration. We are assuming the sloth starts from 0, and then it's going to start moving, okay, but very slowly, okay? So, we know then that my initial velocity is going to be 0. My final velocity is going to be 0,037, and my time is 10 seconds, and I want acceleration. So we know acceleration is change in velocity over change in time, 0,037 minus 0, all divided by 10 seconds. We take out our trusty calculator, and we're going to go 0,037 divided by 10, and it just gets smaller. Now, my calculator has already put it, and I don't know why it disappeared. My calculator has already put it into scientific notation. You don't have to, but as soon as you get numbers where there's lots of noughts before the number in the decimal, or there's lots of noughts after the number, so it's a really big number, scientific notation is actually much better because you're less likely to make a mistake when you write the answer down. When there's lots of noughts, sometimes just because of stress, you either write too few or you write too many, and then the answer's wrong. So I'm going to keep it in that scientific notation. I'll show you what it is out of scientific notation in a second. So that's 3,7 times 10 to the minus 3 meters per second squared, but acceleration is a vector. That means I need to give it a direction, and we're going to assume that it's going forward. For those of you that didn't get it in scientific notation, this is what your answer would be: 0,0037. Both of those are correct. It doesn't matter, though we do prefer scientific notation, especially as we get to more complicated sums later on, and when we look at different sections, scientific notation is just a bit easier, and your calculators can do it for you. Our calculators are amazing. Right. So, our next question. A sloth moves a maximum, you know that, of 0,037 meters per second, and we were using a time of 10 seconds, so that's not going to have changed. But I just needed to add something to this, is that the sloth takes 0,85 meters for those 10 seconds, okay, to get to that maximum velocity. Now they want the sloth's average velocity, and we remember that average velocity is change in displacement or distance over time. So the sloth takes 0,85 meters to get to that maximum velocity, and it takes it 10 seconds, okay? So we take out our trusty calculators, who we like lots, and we go 0.85 divided by 10, and we get 0,085. And it's meters per second, so the average velocity of our sloth as it's getting to 0,037 is 0,085 meters per second, okay? But it's a vector, which means I need a direction, and we're going to assume it's going forward. Really not so bad. So now we know a whole bunch of information about the sloth. Let's look at the tortoise. The tortoise is much faster, okay? So if it takes the tortoise only 5 seconds to reach 0,076 meters per second, they want the tortoise's acceleration. Well, final velocity is 0,076. Initial velocity is going to be 0. And the tortoise is much quicker. It only takes 5 seconds. Okay, so let's work out acceleration. We know how to do that now. Acceleration is change in velocity over change in time. So it's final minus initial divided by 5. So let's just go 0,076 minus 0 is still 0,076 divided by 5. Ooh, not minus, divide by 5. And we get 0,0152. I'm just going to keep all of it. And just like before, acceleration is a vector, which means I need a direction, and the tortoise is going to go forward. Okay, it's not so bad. Now we want average, and actually that distance should be 0,76 meters, okay? So now let's look. The next one says, calculate the tortoise's average velocity. And we know, okay, that the tortoise moves 0.19 meters. So average velocity is change in displacement over change in time. He went 0.19 meters. The tortoise did that in 5 seconds. So we take out our trusty calculators, who we like very much. Oopsie, 0.19 divided by 5 gives me 0.038. So that was his average velocity. At some stages he worked faster than that, in other stages he walked slower than that, but that doesn't matter, that's his average. And of course it's still a vector, so we need to have direction. There we go. One last question. The sloth and the tortoise are now moving at their maximum, and then they say to you, how far will each animal move in 12 minutes? Okay, well, we all know, okay, we've done that velocity is displacement over time. So we're good. If I look at the sloth first, I'm going to call it an S, I would go 0.037 delta x. But now there's a problem. The question says 12 minutes. We can't work in minutes. I have to convert that to seconds. So I'm going to have to go 12 times 60. Okay, so let's work that out. 12 times 60, 720. Please be careful. It's not a difficult question, but where do we end up losing marks? That we forget that that needs to be in seconds. So this is 720. So to get delta x, I'm going to go 0.037 times 720. Again, our trusty calculator, times 720. And we get 26.64 meters. That's very slow, but that's what we expect. And we would do the same with the tortoise, which we're going to do very quickly. He was going 0.076, also 720. And so that would be, because I'm about to run out of time, 0.076 times 720 equals 54.72 meters. And they only wanted that. They didn't need direction because they just said how far. So we've done lots, and I hope it all makes sense. And that's the end of today's lesson. So I'll see you next time. Goodbye.